Hey, what's up, man?
It's not started, right?
No, it's not starting. Hello, how are you?
But why the thing is closed, the other room,
What?
the lunch?
No, it's open. It's just because of the heater. They close it. So, how are you guys doing?
And you
Fine.
doing something here?
No, I'm good. I'm good. Yeah. We have decorated the room.
Here is to
No, that's what, maybe there is a water cup.
Antes house.
Take a cup. There is a water purification.
Yeah, or else upstairs I have some water bottles.
Go
Sure.
upstairs.
I think these cups are fine.
Let's go upstairs to survive.
Yeah. The
Not
TV.
this,
You'll find Patty there. Sure.
I leave my bag.
We are here.
Okay,
Do we?
thanks. Thanks. Um,
Ça va?
ouais, ça va. Ouais. Ça va.
C'est bon,
C'est
attends.
déjà, on est déjà en live là. Donc,
Parfait.
faut partager les liens après. here for the computer, like the
Is
speaker.
it on? You mean for you?
Ah, okay.
Yeah,
No,
it's working.
no, it's there.
Oh.
So you said that, and
Let me see if I
is there a button to cut off the mic? Oh yeah, there's a button directly. Okay, great. That's great.
I can cut off mine.
That's YouTube?
Yeah.
Okay.
It's pretty well.
Yeah, yeah.
Yeah.
Or he tried, or he's trying, but he said he's
Uh,
connected.
Okay, hello, Tybee. Do you hear us? I mean, I don't see him.
He's not a participant. Yeah.
It's not online.
Yeah, send him a message.
Yeah.
And I will try to call him again.
There are two online, Daniele and Murat.
Yeah, no, Daniele and I should be online,
Not is here.
but Daniele should send. Anyway,
Who told me that Murat was in online? Only Daniele.
yeah, Daniele and Murat, and I'm not Murat. I become crazy with you.
No, because I was.
It's Murat.
Online. He's online.
Okay.
Maybe he's there.
Here we have Tybee.
Daniele.
We have two. Abdellah is online also.
Huh?
Okay, but il y a bien deux personnes.
There is
Abdellah.
Hello, Professor Tybee. Do you hear me loud and clear?
Ouais, bah, Abdelhamid, c'est son prénom. Donc non?
It's the same.
I think your mic is cut, but
It's Daniele Pucci.
Okay.
Yeah, Hamid, you can call him Hamid.
Can you hear me?
okay. Now we have Daniele as well. Okay.
Good.
Hi, Daniele. Can you hear us?
Daniele, how
Is
are
it
you?
good? You
Ouais.
can you hear?
No. First.
Hi,
You have to
Taibi.
send the
Yeah.
How
So
are you?
please, Daniele, I ask you to send me a proxy form, so in order for us to sign the report in your behalf. I
Yeah,
just resend it to you. Can you please send us back as soon as possible?
Yeah,
It's signed.
absolutely. So just 1 second, I am trying to. Yeah.
Can't really hear you. I'm sorry. This is...
Do you hear me, Tomas? Tomas?
Why can't I hear you?
Do you hear me, Tomas? Taibi, do you hear me?
Yes, I do. I hear you, Daniele.
Good. Good.
No. On a décidé bien avant.
Turk, can you give me a hand here, please?
Tarek is there.
Daniele, we can't hear you.
Tarek.
I think
Nice to hear
I think he's
you.
His mic is
I
on.
know my actually my sound is on.
But can you hear Taibi?
No, actually I can't hear anyone of them, even though their mics are.
Daniele, can you hear me?
Yes.
Okay.
Anyone else?
You get a document from Thomas. You
Yeah.
have to sign it and you send it back, please, right now.
So I
No,
think
yeah, yours is working.
it's right. Right?
Yeah, check. Wait, can you have settings? In settings, check the input sound.
Yeah,
If can you check it? Wait,
my input sound. You mean?
yeah, like in going to settings. Yeah,
Yeah, there we go.
sound settings exactly.
There you go.
Proxy. Ah, dia
Yeah,
voce.
Okay.
Yeah.
Okay.
Talk.
Can you? There we go. Now I can hear you.
Okay.
Ah. Okay.
No, pronoun.
Now we got it. Okay, great. Okay, thank you very much for joining. Okay, now that we got your sound, I'm gonna.
No, before.
Daniele, have you sent?
Yeah. I'm doing it now.
Okay, he's doing it now.
Okay.
Okay.
So don't worry, I'm not gonna screw it up everything. So yes. Toma. Lopez de Oliveira. Toma, I talked about you with Robert Mahoney that I met recently. Yeah.
Great. Okay.
Le usa Sandra 4.
Yeah, maybe leave
Shall we
that.
start?
Yeah, okay.
So let's start. So I'm Tomas. I'm a research director at INRIA, and I'm to be elected unanimously president of this jury. So the jury will be composed by Rita Cunha, associate professor at the University of Lisbon, Pascal Morin, professor at ISI in Paris, Abdelhamid Taibi, who is professor at Lakehead University and he is online. Daniele Pucci, researcher at Istituto Italiano di Tecnologia online. And we have Murat Bronz Meddekom at ENAC. And finally, the research directors, Tarek Hamel and Claude Sanson. Tarek, professor at Croises, and Claude, director of research emeritus here at Croises. So you have 45 minutes to make your presentation.
Okay. So, good afternoon, everyone. My name is Tomas Lopez Oliveira. I'll present my work entitled Control of Convertible Vehicles with Vectorized Thrust, done here in Oscar system at I3S. So this presentation will begin with a brief introduction of the topic that we're going to address in the thesis. Then I'm going to give an outline of the contributions. Then I'll dive into each one of these contributions. This will be followed by a presentation of the results that we obtained along the thesis with a short video. And finally, I'll give a conclusion with some future remarks. Remarks for future work, sorry. So what are convertible vehicles? So convertible vehicles are basically aircraft that can hover like helicopters, but they can also fly at high speeds like fixed-wing aircraft. So they basically use their wings like airplanes in order to generate lift when flying at these high speeds. These aircraft have been developed since the 1950s. However, very few of them have reached the operational phase. So here are some examples: the Osprey, the Bell Osprey, the Harrier, and the F-35 fighter jet. So nowadays, with the growing drone market, a large amount of convertible vehicles are now available to the general public. These convertible vehicles come in all sorts of configurations. We can maybe classify three big groups here today. So our first one, so basically this classification will vary in how these convertibles convert from the hovering flight to the fixed wing flight. So our first group is a tail sitter. So these aircraft, they take off while sitting on their tail in this vertical position, and they convert to the fixed wing flight by tilting the entire body from this vertical to the horizontal position. Another group of vehicles are the tilt wing and motor aircraft. So these aircraft have structures of the wings and the motors that can tilt jointly. So they begin in the takeoff in this vertical position, and then they also convert to the horizontal position. But the difference is that they can keep actually the fuselage at level at all times. And finally, the class of vehicles that we're interested in here today, which are convertible vehicles with vectorized thrust. So these are basically fixed-wing aircraft that can produce a thrust vector in the aircraft's vertical plane. So to give a better idea of this, so a large class of these vehicles are actually tilt rotors, like the ones I have here on the right. So these are the drones we use during this thesis. So what are tilt rotors? They're aircraft that have motors that can tilt. That means they can change the direction where they're pointing to. And the sum of the forces of all of these motors, they will produce a thrust vector in the aircraft's vertical plane that we will represent here today by this vector t. And it will have an angle in that plane that will be described here by this angle theta. Another type of convertible vehicles actually doesn't have tiltable rotors, only has fixed motors, but they're fixed in different directions in the body frame, like the quad plane I have right in front of us today. So in the same way, by coordinating the forces of all of these motors, we can produce this thrust vector in the aircraft's vertical plane. There are other examples of quad planes that I put here on the image that I put in the image here that you can see on the right. So other from the thrust force, convertible vehicles also produce an aerodynamic force. So traditionally in aeronautics, this force is decomposed into two orthogonal components. A first one is in the direction of the air velocity, and it is actually opposed to it. and it's called the drag force. So this force resists the motion of the aircraft. And then we have a second component, which is orthogonal to the air velocity vector, which is called the lift component, here represented by FL. So this is the main force component responsible for overcoming the weight of the aircraft while it flies. So among the various characteristics of an aerodynamic force, one well-known one is that it varies with the square of the air velocity. So that means the norm of this vector VA here. And another important characteristic is that it is highly dependent on the orientation of the aircraft with respect to the airflow. So this orientation is usually described using two angles. A first angle is the angle of attack. That will be quite important for this presentation today. So the angle of attack is an angle related to the vertical component of the air velocity in the body frame. So this component over here. And then we have the side slip angle, which is an angle that is related to the lateral component of the air velocity in the aircraft's body frame. Most aircraft with wings, they are actually designed to fly in a balanced flight condition. So in this condition, we're going to have this lateral component of the air velocity 0. And while flying in this condition, we're going to have all of the components of the air velocity of the aerodynamic force found in the aircraft's vertical plane, as shown here in this image here. And then they will be mostly dependent here on this angle of attack. So a big topic in actually the research of convertible vehicles is actually the transition between the hovering phase to the cruise the transition between the hovering phase and the cruise phase, where we're going to have the wings working to lift the aircraft. So most approaches, they actually involve two separate controllers, one controller for the hovering phase, another controller for the cruise phase. And the transition is just going to be done by abruptly tilting the thrust vector from the vertical position to the horizontal position. So in 2018, the Oscar Assist team, they proposed a novel approach, which is a unified approach, which the goal is basically to combine in a single controller, something that can contemplate all of the phases of convertible vehicles with vectorized thrust. So this approach will enable then a smooth transition of the thrust vector from the low speed phase to the high speed phase in a way that we have this single control. So the main goal of this thesis was actually to complement some of the things that we're still missing in order to apply this approach in practice. I'll comment on them soon, and to validate the approach in practice. So to model actually the aerodynamic force for control is actually quite complex, especially for convertible vehicles, because these aircraft, they go through actually conditions that are quite different from fixed wing aircraft. They can be submitted to high angles of attack, and modeling the aerodynamics in those conditions are especially difficult. Another thing is that these models will have other uncertainties that will come from the fact that we have the flow of the motors on the wings. So all of that will create a lot of uncertainties that make it quite difficult to model these things in practice. So in order to deal with this, the approach proposed in 2018, here in the lab, uses a simplified but yet representative aerodynamic model to model the aerodynamics of the aircraft. So this approach applies to all orientations of that the aircraft can have. This is actually quite different from traditional linearized approaches that use the lift and drag decomposition, where they can only be applied at small flow angles or small angles of attack. So this approach, we can have all of these orientations, and it was initially applied to axisymmetric vehicles such as rocket-like vehicles, the ones I represent here. And actually, an important thing about this approach as well is that it applies well to bodies with symmetry. So in order it considers actually that the body that we're using has some symmetry properties, and that's actually from where we get this application into all orientations. So for example, in the case of a rocket-like vehicle, we're gonna we can apply this cylinder idealization in order to make this assumption on the shape of the aircraft. In the case of an aircraft with fixed wings, the idealization used is a disk representation like the one I show here. And basically this disk will represents this disk idealization is used to represent the aerodynamic force of the aircraft in a balanced flight condition. So the approach proposed in 2018, it addressed theoretically all the main flight phases of a convertible vehicle. However, there were still some practical issues that need to be addressed. So the solutions to these practical issues are going to be the main contributions for the thesis I'm presenting today. So first of these issues are control issues. So the approach proposed in 2018, it actually depends on the determination of the air velocity, the air velocity, and the main problem with that is that when we go to low speeds, we end up we get near to a singular position, which is to a singularity, that will take place at VA equals to 0. So that means the control actually cannot be defined near that singularity, and it needs to be complemented in practice. Another issue regards the production of torque. So as we see today, convertible vehicles, they can produce torque using their motors, but also their control surfaces. And in order for us to show that this approach can be worked out in all of these configurations that we see today, we still need to figure out how to coordinate all of these actuators in order to produce a torque to control the orientation of the aircraft. So as I said, the control approach depends on this determination of the air velocity. So we need to have that estimated or measured on board. So unfortunately, on small aircraft like the ones we see here, they all have this sensor here, which is called a pitot tube. And the pitot tube, it can only measure actually one component of the air velocity. So that means that the other two components must be estimated. And thus we still needed to analyze better in practice if we could estimate well this air velocity for this thesis. And finally, I said as well that one of the goals is to validate the approach in practice. So that is usually done in two phases. So here we worked out a lot of simulations in a first step in order to evaluate already some of the robustness of the controller. And then in a second phase, we take this to flight tests where we really test it in a real-world environment. So during these tests, we want to evaluate the robustness of the aircraft, mainly for example, for modeling errors, because as I said before, we're using a simplified model for the aerodynamics. And another thing is that these, as I said, convertible vehicles go through a large flight envelope, so the conditions of flight can vary a lot. And for smaller aircrafts like the one we have here, another important thing is actually to be robust to wind perturbations, since a small wind speed, as measuring, for example, 7 meters per second, can really change the phase of flight of the aircraft. So now to dive into the first contribution, which is the control at low speeds. And in order for us to understand it better, I'm going to make a recall here of the approach proposed in 2018. So back then, let's in order to simplify this presentation, we're going to assume here we have two types of inputs. A first input is the thrust vector of the aircraft itself. It's going to be defined by this tilt angle theta and this thrust intensity T. And the second type of input will be the aircraft's orientation, which will be described here by these vectors I, J, and K. So the underlying assumption here that we use in order to define this second input here is that we know how to create the torques to make the aircraft's orientation converge to a desired orientation. And so please consider for the next slides that these I, J, and Ks here are actually the desired vectors of the desired orientation. So if we write out the Newton equations for a convertible vehicle, we're going to have this equation here with the weight force, with the aerodynamic force, Fa, and the thrust force here in the vertical plane, described here using these vectors I and K, and the thrust inputs I mentioned before. And if we write out here our aerodynamic force, so as we can see here, this aerodynamic force is decomposed into the three components of the body frame. So this is a different decomposition that I showed previously, which depended on the direction of the air velocity, so the lift and drag decomposition I mentioned before. And so for the first component that we're going to have here on the direction of I, it will basically kind of work like a drag component. It's going to resist the motion of the aircraft in that direction. And then we're going to have the second component on a direction opposite to K, which is also going to kind of work with as the lift force. So it will be mainly responsible to overcoming the gravitational force. And we're going to have this constant here, C0 bar, and this constant C0, I forgot to mention. So C0 bar here will be much larger than this constant C0 here. So we can have actually a much, because the lift force can be actually much stronger than the drag force. So that's why this constant is larger. And finally, we're going to have this lateral component here on the direction J, which is the component that we want to make sure it is close to zero in order for us to have a balanced flight. So the image that goes with this formula here for the aerodynamic force is that disk idealization that I mentioned before in a balanced flight condition. So we want to control the aircraft's translational motion, and we're going to do that by using this auxiliary control input here called Xi. So if we just add and subtract these terms here on Xi on our Newton equation, thus not altering it. And we're going to define now these vectors A, D, and E, which are just going to be there to alleviate a bit the notation. And so A will be dependent on this auxiliary control Xi and the direction of the gravity. And we're also going to have D and E depending on A and VA. So if we replace these vectors here and our model for the aerodynamic force in the Newton equation, we can rewrite it in this form over here, where we have it, the terms in each one of the body vectors of the aircraft. So if we set the thrust inputs to the values I show here, which are dependent on the directions I and K, and those vectors D and E, we get to set these two terms here on I and K to 0. And if we set the vector J, so the vector of the orientation J, to the value that we show here that is orthogonal to VA and to A, we get to eliminate these two other terms here. And by doing so, we get to this much simpler equation to work with, which is V dot equals to Xi. And the Xi can then be used to design our control for attaining our desired control objective, such as stabilization, path following, or tracking. And we can also use classical PID techniques. So I mentioned in the previous slide that we have this vector J that we defined orthogonal to the vector VA. We also know that J is a body frame vector. So it has to be orthogonal to I and to K. So that means I and K and VA will be in the same plane, and we can actually define the vectors I and K that haven't been defined yet using a desired angle of attack. So two possibilities were actually explored in the work in 2018. So a first one was to determine the angle of attack that minimizes the thrust. So why is this important? Well, if we could actually, in practice, have infinite amount of thrusts, we would really care about the orientation of the aircraft. But as the airspeed increases, we're going to have a larger drag force, and we would like to keep that force as small as possible, so we can still have enough power to move the aircraft. Well, the second possibility was actually to impose a tilt angle for the thrust vector first that could, for example, depend on the air velocity, and then figure out which actually work out the angle of attack that satisfies the dynamic constraints that I had before, and thus determine the vectors I and K. So here on the right here, I have an example of the evolution of the angle of attack and the tilt angle in the transition in horizontal flight, just to show how it looks like. So this, I here have the first case, which is the computed the angle of attack that minimizes the thrust. So we can see we have a nice smooth curve of the angle of attack from low air speeds to high air speeds. And as we expected as well, in order to minimize the thrust at higher speeds, this angle of attack is low, so we can have a low drag force. However, we have a little inconvenience actually at low angles of low air speeds, that the angle of attack actually is quite large. So in practice, this would mean that the pitch of the aircraft would be very high. And this is not really convenient, because if we ever have a wind gust at that slow speed, that could really destabilize the aircraft, since the aircraft will be pushed by a strong drag force. So ideally, we would like to keep the nose of the aircraft down in that phase if we can. So, so now moving on to the control at low speeds. So at low speeds, we can't really use the framework that we had before for defining the vectors I, j, and k, because they become singular when VA equals to 0. So around in the neighborhood of that singularity, we have to redefine the control strategy. So we are going to define a control strategy that is not dependent on VA and is not dependent also in the aerodynamic force. This is not much of a problem, because at that neighborhood of the singularity, these aerodynamic forces are negligible. So the approach adopted here would be to define only a desired pitch angle in order to so we can control the nose of the aircraft. We will also still, of course, satisfy our control objective. So we can do both of these things by stabilizing only one vector of the orientation. So that would be this vector k. And how do we build this vector? Well, we define this auxiliary vector ID here, which will be constructed using this desired pitch angle theta d and the aircraft's current yaw. So so then we compute this vector k by computing this orthogonal projection of this vector A, which contains our auxiliary control input, along this auxiliary vector ID. So important thing here to note is that, well, since we're taking there the heading of the aircraft, the current heading, that means that the yaw, the degree of freedom of the yaw of the aircraft will be free at this moment. So once we get out of the neighborhood of that singularity, we can then once again have a well-defined air velocity vector, and then we can start. We can actually complement this vector k with a second body vector, which that can be orthogonal to the air velocity and the vector k, and in that way we can slowly align the aircraft in order to go back to a balanced flight. And since we can now define this vector k and this vector j, we can then define the entire frame using this cross product here. Okay. So I did not go into the details of how we do the orientation control. This can be found in the first paper of this thesis, 2023. So there we explain how to obtain the asymptotic stabilization of the third vector of the orientation of the aircraft to that desired vector k that I showed before when we are in this neighborhood of the singularity, and how to obtain as well the asymptotic stabilization of the entire orientation of the aircraft once we're out of this neighborhood of the singularity. So once we now have a control approach for low speeds and for high speeds, we would like to now define a transition between these two control strategies, and the best would be that this transition is also smooth. So in order to do that, we're going to associate an angle of attack to that frame that we can define once we're just out of the neighborhood of the singularity, and this angle of attack can be computed using that vector k that I mentioned before. And then for high angles of attack, well, the angle of attack we can use, for example, the angle of attack that minimizes the thrust. And in order to combine both of these in a smooth way for a transition between one to the other, we can use this convex combination here that uses this function lambda depending on the airspeed. So this will basically give at slow speeds under a given threshold an angle of attack that equals to alpha L defined there. And once we reach a higher threshold, we'll transition to an angle of attack that worked well for the high speeds. So as we saw here, the approach depends a lot in the air velocity vector. So we need to estimate it. So this thesis, we looked into that in order to start this discussion. We can define the air velocity as this vectorial subtraction between the inertial velocity and the wind velocity represent here. The inertial velocity usually is estimated on board. We can also measure it using GPS measurements. The velocity of the wind, on the other hand, that is usually we cannot measure it directly. So we actually have to think of another way of approaching this air velocity estimation or measurement problem. So one way is to directly measure it using various types of sensors, for example, multi-probe pitot tubes or wind vanes. The problem is that, as I mentioned before, most small aircraft like these ones, they can only accommodate only one pitot tube, which will only give us one component of the air velocity. So the remaining components, we're going to have to estimate them. And there are basically two big types of methods out there. One type of method is a model-based method. So these methods, they use the dynamics of the aircraft in order to deduce the air velocity. The problem is that while doing so, we're going to need a high-fidelity vehicle aerodynamic model, which is actually quite inaccessible for low-cost aircraft like the ones that we have here. Another type of model, another type of estimation algorithm is our model-free algorithm. So these algorithms, they're only based on kinematic equations. The state-of-the-art methods nowadays are actually to use a cascade of observers. So a first observer to estimate the inertial velocity and the orientation of the aircraft. And then this information gets passed down to a second observer that will combine this information with pitot tube measurements while assuming that the velocity of the wind is slowly varying or is constant. So this second estimator, it will actually estimate the velocity of the wind. And once we have then the estimate of the inertial velocity and velocity of the wind, we obtain our velocity, our air velocity. So in the second in the second paper that we done in this thesis, we propose what we call a pitot tube air velocity aided attitude observer. So this means that in this type of observer, we're actually also going to get we're not only going to estimate the air velocity, but we're also going to get some information on the vehicle's attitude. So this will be a model-free method in the sense that we only use kinematic equations. And another novel feature is that we're going to use a minimal sensor suite, which will basically comprise a gyroscope, an accelerometer, and pitot tube measurements. So the IMU will give us the specific acceleration in the body frame, the angular velocity in the body frame. Pitot tube measurements will give us the measurement of the air velocity along the aircraft's first axis there. And here we're also going to assume that the wind is slowly varying. So, and if we do so, we can write this equation here of the air velocity in the body frame, as we see here. And where we have this rotation matrix R that will represent the orientation of the aircraft. And when we write R transpose E3, this is actually the orientation of the gravity expressed in the body frame. And the dynamics for that vector can be expressed by this first equation shown here. So the observer dynamics can be represented by these equations here. So these are basically a copy of the system with the correction terms. Here, delta 1, delta 2, and delta V. So the approach for designing these terms is that we adopted is a Riccati observer design approach. So there we can actually show, demonstrate that we have a local exponential, local exponential stability of the origin of the observer errors. But we have that under the assumption that the wind is slowly varying, as I mentioned before, and that we have a persistent excitation condition on the aircraft's orientation. So for the case of a aircraft like the ones we have there with a pitot tube on the direction of I, this persistent excitation condition on the orientation is basically the motion of the pitch of the aircraft and its yaw. But if we had other measurements, say on the directions J and K, we could reduce this persistent excitation to only a pitch and or yaw. And if we had measurements along the three directions of the body frame, so measurements of the air velocity along those three directions, this persistent excitation condition actually would no longer be required for the convergence of the filter. Another thing that was done during this PhD, but not during, but it's not in the thesis actually, is that we also investigated inclusion of barometer measurements in the observer approach. So in this case, we have to add another assumption. And this assumption is that the wind velocity is that the wind blows horizontally, that we don't have a vertical component of the wind. And the good thing about including the barometer in that case is that we get to reduce the persistent excitation from the pitch and yaw to only a condition in yaw. So this is actually more easily attained in a flight of a convertible vehicle. So in order to test this approach in practice, we evaluated the approach using data from a flight of a convertible vehicle. So, and we did that in an indoor environment. The main advantage of doing it in such environment is that we can assume that the velocity of the wind is zero. And that way, if we have an estimate of the inertial velocity, it will be equal to the air velocity. So in this test, we had on board another estimator that could give us an estimate of the direction of gravity. So here is the error of, or the estimate of the direction of gravity with respect to that estimate as well. So we can see that we attained practical convergence. And we also compared here is the norm of the error of the inertial velocity that we had estimated on board with our estimate of the air velocity. And we can see as well that they're quite close during this experiment, and the observer also converges quite fast. Here on the right here, I have each one of the components of the air velocity vector compared with the components of the inertial velocity in the aircraft's body frame. So now to move on to the last parts of the contribution of this thesis. So in this will regard the torque distribution or the production of torque. So we start off by actually defining a control policy in order to allocate the torque that we want to produce to the motors and to the control surfaces. So we represent here by gamma A, the torque of the control surfaces, and gamma M, the torque of the motors. And this is done again by this convex combination here, using now this function lambda bar, which depends on the airspeed. And the idea behind it is basically that at slow speeds, we want to use the motors in order to control the aircraft's torque. And as the airspeed progresses and we get more dynamic pressure on the control surfaces, we're going to use we're going to start using the control surface. So by using this law here, we have this smooth transition between for the allocation of the authority of producing torque from the motors to the control surfaces. And once now we have the amount of torque that we want to produce with each one of these actuators, we can then work out how we're going to distribute them among the various actuators of the aircraft and taking into account their position. So this was done, for example, so this is basically illustrated in this schematic here for the E-flight vehicle. So once we have the torque for the control surface, we're going to distribute them among these two control surfaces here. And for the motors, we also did that for E-flight, taking into account the fact that it has tilts. So this was done actually for all of the aircrafts that we see here today. And once we know the torques of that each actuator actually has to produce, we can then now have to work out how we're going to actuate this this given actuator. So for the control surfaces, this means actually establishing the relationship between the deflection angle of the control surface and the desired torque. So we do that again using the disk idealization model that I mentioned before. So we model each control surface as a disk as represented here. And from there, we can then compute the desired angle of deflection given a desired torque. And for the motor case, well, we would like to actuate also the motors as best as possible. So in order to do this, we identify the relationship between the PWM signals sent to the motor's electronic controller and the thrust they produce. So this was done using the test bench, and we got to identify this relationship quite precisely as illustrated in this graph here. So as I mentioned, once we now have this approach, we would like to test it in simulation, exhaustively in simulation and experimentation. So our first phase is the simulation phase. In simulation, we would like to have something as close to reality as possible. So we'd like to have a model of the aircraft that matches reality as best as possible. In this work, we've done that by extending the model that we use to control for control in order to add other effects that were not present there. For example, the aerodynamic torque and the stall effects. So we do that again by using the disk model representation. So basically, we represent the flat surfaces of the aircraft by several disks, as shown here, and the fuselage of the aircraft by a axisymmetric shape that will also be long. Sorry, I got the mode, the word. But for example, a cylinder or a ellipsoid. A slender figure such as a cylinder or ellipsoid. So, and for the stall effects, as you remember, we had those coefficients C0 and C0 bar. So we can define these coefficients in such a way that we put them as a function of the angle of attack. And that way we can change the behavior of the aerodynamic force when we reach high angles of attack. For the motor force, we actually adopted a similar approach, and the goal there was actually to use to represent the force of the rotor blades. We use the disk model representation. So that means each rotor will have its own air velocity vector represented there, VA. So as it turns, it will create this aerodynamic force that will push the aircraft. And by doing so, we arrived also at the expressions not only for the motor force itself, but also to expressions that can represent the motor parasitic forces, which are present in reality, and we would like to also have that in simulation. So just get it. There we go. So another part, an important part of this thesis was to work out control modes for the convertible vehicles that we have today. So today I'm going to show a video with three of these control modes. Our first one is the semi-automatic mode. So this is a mode where the pilot will control using an RC controller a desired inertial velocity. So in this case, the auxiliary control input that I mentioned before will be computed for a velocity tracking control objective. And then I'm going to show two other modes, which are the waypoint navigation and the circle modes. So these two modes, we're going to have that auxiliary control vector computed for a path following control objective. So in the video I'm going to show here, we're going to have the Cruiser aircraft. It's going to start flying in a semi-automatic mode. And on the top right here, I'm going to have the airspeed and the inertial speed of the aircraft. So you can compare both. You're going to see that they're not going to be the same because we have wind perturbations. And on the second plot here, we're going to have the tilt angle of the aircraft, of the motors, sorry, and the desired angle of attack on the bottom. So I can see as it accelerates here in the semi-automatic mode, from low speeds to high speeds, the tilt angle went from 0 to 90 degrees. In this other video here, we have the aircraft in its back transition. So coming back from the fixed wing flight with the tilt angles starting at 90 degrees, and then they're going to come back up. You're going to see here on the angle of attack that's going to increase up to 20 degrees in order for it to create enough drag force in order to stop. And at the same time, we'll be using also the tilt in order to produce a thrust force backwards. So you see there the tilt dropping. So here in this video here, we also put the estimated angle of attack in order for us to compare those two frames, so the desired frame and the frame of the aircraft. So you can see it's it's tracking that quite closely, which means the orientation control is doing a good job. So now in this video, we have the waypoint navigation so the goal here is to follow this path that's connected by the waypoints. And the goal is also to follow it with a given inertial speed of 10 meters per second. So you can see that the speed is quite well followed in the first graph over there. At this low speed, the tilts are still not fully lowered, but they're over there at 20 degrees. And now we're going to increase the desired speed up to 15 meters per second, as you can show down there. So you can see that the speed of the aircraft increases and the tilt angle, the tilt angle lowers to 90 degrees. That little drop that you saw there for the tilt angle, that means it got lifted up. That was just because the aircraft needed more force to perform that sharp curve over there that in the trajectory. So for the circle mode, the objective here is to follow this circular path, inclined circular path, which is actually quite difficult to do with another type of aircraft that's not a convertible. And here we want to follow this path with the desired speed I'm showing there. So now it's up to 12 meters per second. And during this flight, you'll see that the angle of attack is varying at all times, as well as the pitch, the tilt, in order to attain that control objective. So we applied this to other aircraft, such as the Ranger, as shown here, which is a small version of the cruiser aircraft that is there on the back. We also applied this to the Cypher aircraft, which is an aircraft with 4 motors, 2 on the back that tilt, 2 on the front that are fixed. Another aircraft was the E-Flight. So E-Flight is different from the cruiser in the sense that it only has 2 control surfaces. So it has less actuators than the cruiser. And the last drone I have here is the fighter. So the fighter here in the semi-automatic mode. So it's accelerating from low to high speeds. And finally, it in a back transition coming back from the semi-automatic flight and ready for the land. So now to conclusion and some perspectives for future work. So recapping now, the main contributions of this thesis were basically the extension of the control solution down to the low speed. And that way we can comprise all flight phases of convertible vehicles with vectorized thrust. Another contribution was the novel observer that we proposed for the air velocity estimation that uses a minimal sensor suite and can be used for the flight of convertible vehicles. And finally, we've been able to validate and assess the robustness of the control approach in practice, applying it in several vehicles. And some perspectives for future work. Well, one of them is to continue experimentation in other platforms. We got to test quite well Cruiser up to now. We're still working on it, Fighter as well, but there are still other configurations that they still need to be better investigated. We still would like to learn a lot more from these experiments. Another thing is investigate methods for tuning the gains. So basically for the orientation, we have a sort of a high gain control. And the gains actually can change a lot. The ideal gains that we use, they can change a lot depending on the flight regime. For example, the gains that we use for the control of the control surfaces at high speeds are not necessarily the optimal gains for the control of your rotation using the motors at low speeds. And a third aspect is investigate further torque distribution policy. So, for example, another torque distribution policy could, for example, take into account the saturation of the actuator. So, for example, if we saturate the motors, we could use the control surfaces in order to complement the action of torque. Another idea could actually be to investigate in more depth the efficiency of each one of these actuators during those various flight regimes, and thus try to get a bit more refined version of this torque distribution policy. So I thank you very much, and I'll be open for questions now.
So we have now time for question. We will start with Rita Cunha, reviewer of the Thesis.
Good afternoon, everybody. I'd like to start by thanking the supervisors, for the invitation to be here. It's an honor. And I would like to start by congratulating the candidate for reaching this stage. There's still a little bit more just for a small discussion here with the panel. I'll start just by saying a few words about the document, the thesis, to say that I enjoyed very much reading it. I learned a lot from the thesis, and I think that although it's not a huge document, it pays off from our side, from my side, not to be so long, because we can keep focus on what's written, and it summarizes very well the contributions, as you did over here with the presentation. I think that it was very clear, and the contributions of your work are well explained, and that's very good.
Thank you.
Okay, so but I should pose some questions. I'll start with following the structure of the thesis, and also your presentation with the parts on the, maybe I'll skip the models, because I'm going back and forth in my thoughts, sorry. I have a question regarding the controller and the control structure that you use, but it's also related to the model anyway, so it's two in one. So you're using a hierarchical control structure, I would say, and here you even put the orientation as if it was the control input, right? You skip that part in the thesis where you make the distinction between the two.
Yeah.
And I think that's fine. But I was wondering if so you're saying that, okay, then there's a controller that will take care of taking the orientation to the desired orientation using torque control, and you also talk about the torque distribution and how to do that. But I see many different models, and I was wondering, and I don't think that was very much discussed in the thesis. I'm just thinking, if you have a fighter or if you have a cargo airplane, the center of pressure is in different places, so that it has a lot of implications for the dynamics of the system as a whole. And how does that impact the approach that you follow?
Yeah. Okay. Thank you. Thank you for your question. So indeed, each aircraft will have its own aerodynamic behavior, something that is not in the model used for control is the torques, the aerodynamic torques. So as I said, the approach is actually based on this high gain idea for the orientation control. So so basically we would like to actually use all the actuators that we have in order to produce this torque in such a way that it can satisfy that objective of aligning the two, well, getting our reference frame converging to our desired reference frame. What I can say is that, well, for the various vehicles that we have here, even though they have these different behaviors, these usually translate to different gains, and also to different strategies in order to define actually the control polys that I mentioned before. So, for example, some aircraft will be actually easier to control at low speeds, because basically you're going to have when we're in the transition phase, because they won't produce much aerodynamic torque, and that way we can use, for example, the motors for longer. But that, well, it really depends on each aircraft, I would say, in that sense. Yeah, I don't know if I reply that very well, but yeah.
I think that you can still use the same strategy for all. It's just a matter of tuning the
Yeah, I would basically summarize it as that. I mean, as I said, the main difference you'll see between the gains used, actually the controllers used for each aircraft will be basically the gains. Well, yeah, that was some of the things that we spend a lot of time as well, finding good gains that in order to make them work in practice.
So it's always let's say a balance between what you put in the inner loop and the outer loop physics. You cannot use the same outer loop for all.
Well, the outer loop would be this control of the translation, right? So, and that's actually something that is quite similar for each or the application of each aircraft. I would say well, really the main difference was in selecting the gains and also defining when we're going to initiate the control at higher speeds and when we're going to end the control at low speeds and we're going to begin the control at high speeds. So the choice of these parameters, they actually depend on each aircraft. But I would say like the good thing is that we managed to find these parameters for aircraft that are quite different, like the fighter and the cruiser aircraft.
One thing that puzzled me, since you talked about it, that transition between the controller for low speeds and then the other approach, are the figures, maybe you don't have them here, but maybe slide 17 will be enough
Yep.
to pose my question, which is, oh no, so 15, sorry.
15, okay.
The one where you have the angle, yeah.
Okay, yeah.
The plots for the angle and the path. Remember that in the thesis, you show a few plots where you show the transition, right?
Yeah.
From angle of attack 0 for low speeds, and then you have different curves depending on the parameters, the way that you choose the parameters. My question here is, it was puzzling to me, and I must say that I didn't fully understand how this was done, which is that you said that for the low speed controller, you were using a desired pitch angle at theta D, right?
Yeah.
And for the figures that you had there, the theta D was 0. But then I see this transition in the angle of attack. And shouldn't they be related or more or less the same in those situations?
Yeah, so let me I have a similar plot to that one here today. So that would probably help. So the control strategy for low speeds, we're going to do it in the neighborhood of the singularity VA equals to 0. So, and as I said before, the goal is we're going to control the aircraft's pitch, and we would like to set it low, so that way we not be that vulnerable to wind gust perturbations. So in this example here, I have the same example where we're doing a transition in horizontal flight, and it's the same one that is found in the thesis. So for the airspeeds below the threshold that we define as the low speed control strategy, well, we don't define an angle of attack in that zone, but as we start accelerating and the airspeed starts building up, we can then start defining an angle of attack. And since that, so here, this is a horizontal transition, right? So if it's a horizontal transition and we began with a small pitch angle, that means that the angle of attack associated to the frame, that low speed frame, as the aircraft starts getting into this high speed domain that I call here, is going to be actually quite low. So that's why it begins at a low value here, and then it's going to slowly transition to the high speed solution that here, in this case here, is the one that minimizes the thrust. And then we have this angle of attack that remains at low values as soon as we can define an angle of attack for the control. Yes, so the pitch will change. It will only be 0 and the low speed domain. And yeah, so it's the blue zone. So I didn't even want to put a curve there because it doesn't really make sense to define the angle of attack in that phase. But as soon as we get out of that phase, what we would expect is that the angle of attack is actually quite low. It will also depend on the wind velocity, of course, but we would expect that angle of attack will be quite low since the pitch was already low before.
Say, and you showed the results for an indoor flight experiment. I think it was
Yes.
indoor.
Yes.
Can you give a little bit more details about how this experiment was done to check, or how did you obtain the ground truth for comparison?
Yes. So we did this indoor flight experiment with the E-Flight aircraft over there. So on it we had the PX4 control system, and in it we have an estimator for the aircraft's inertial speed and for its orientation. So we having the data from the sensors, then we could test our algorithm and compare it with these estimators. So the goal there is that since we're in an indoor environment, we have the velocity of the wind that we can reasonably assume to be 0. So then the air velocity can be compared with the inertial velocity. I must say as well that we were kind of lucky in that experiment because we got GPS measurements even though we were in an indoor environment, in order to verify, or at least to have some guarantee that the estimate of the inertial velocity actually makes sense. I compared it with the measurement of the pitot tube. So since they were quite close, I said, well, this can then be used as a proxy in order for us to evaluate the observer.
About the experiments, I think that it's impressive what you've done, both on the part of the simulations and all the models and all the modeling that was involved in this part, and then of course going for the experiments with not just one vehicle but several different ones to really showcase and demonstrate that this can be applied and you can obtain good performance. But it puzzled me that the simulation models, I think that you talk about 5 or 6 simulation models, and then they don't match the real vehicles. I got that impression, but maybe I'm wrong.
So don't match it in what sense? Sorry, it's just so I.
They're not the same. It's not the same motor, the same fuselage, whatever.
Yeah. I mean, indeed. I mean, if we could actually, another option would be if we could have a much more powerful simulator that could really model well the aerodynamics. I would say that the approach that we do for simulation is still a very simple one, right? But I think the main thing is that we tried to. The goal was just to really be able to already test the robustness of the controller against these effects that are not in the control model, and that way we could already assess some things before we went down to the flight experiments. I could also say that, well, simulation already with these more simplified models, we could already deduce quite interesting things and already get some idea of the gains as well before we fly. So it was, but it's still a much simpler model than I think we would have in other simulators.
Question about the sorry, If you go to your final slide on the perspectives again.
Yep.
So you have here the main contributions, the perspectives for future work. But I would like to, if you could add some bullets on what was really difficult to get.
Like
what you propose to do. Very general question. Very open question.
Yeah, well, I would definitely include the methods for tuning the gains, because that's was one of the things that we had a very a hard time trying to work out. Especially the gains responsible for the orientation control. So as I said, the regimes of flight, they will vary, and well, the gains on one regime will not be probably the best for the other. But I would also add that well, some configurations, they sometimes have things that were not actually in the model. So we spend a lot of amount of work as well with eFlight. We weren't able actually to validate the entire flight domain for eFlight yet. So the white drone on the right there, and but that's basically because we had things that were not taken into account, like these motor wing interactions. So once you have those things interacting at the same time, it's sometimes hard to know if it's really something because your model is limited, or is it really just because you didn't find the correct configuration of gains yet in order to make it work? So
Much about tuning gains. Do you think that it would be possible to design an auto-tuning algorithm or method or whatever?
Well, yeah, I'm not sure exactly. I don't really know really well. To be honest, I really don't know really well algorithms that do that automatically. But yeah, I mean, I think even for us that we're trying to work out the physics, it's kind of hard. So to come out with an algorithm that has these intuitive ideas, well, you first have to have these intuitive ideas in practice and kind of what direction to put it to set the gain. So I would say that would be probably a second step once we kind of really understand how to do this thing in a better way.
Okay, thank you. So next will be Pascal Morin, the other reviewer.
Okay, thank you. So first of all, I would like to thank also for inviting me to this PhD defense. I would like to congratulate you for both the work, which is very, very nice. I was really impressed by the result, and also the experimental, especially the experimental results, which I find really really exceptional and really a step in the state of the art. And also, I would like to congratulate you for the presentation, which was really clear, which summarized very well all the methodology, the contributions. So very, very nice presentation. So I will have a few questions. The first, to start with a few questions on modeling. Also, I know it's not the main topic of your thesis, but still, I mean, there are models. You use models. You also introduce some ideas in modeling. So I will have a few questions like that. So from what I know, the modeling of propellers that you propose is new. In fact, I didn't see it before. And of course, there is something that you don't take into account, and I don't know if you could, or if you didn't, if you thought that it was not useful to do that. It's what typically people do when modeling propellers is take into account the induced velocity. So you don't speak at all of induced velocity. So do you want to add a few words about that, or is it something that you considered at some moment, and you said it's useless, basically, or so can you say a few words about that, and maybe but comparing also the models with what we can find in the literature.
Yes, well, thank you for your question. So, yeah, indeed, induced velocity is used in other approaches with the blade element model approaches. No, actually, well, we didn't really think about that when this was being developed, because well, we wanted still some I think the first goal was also, in the first sense, could we actually use these more simplified modeling equations for the propulsion parasitic forces and maybe try to compensate them in control. Well, try to work out some solutions, but we didn't really go much further in that direction. And then, well, we could still use these things in simulation or to make the simulation more realistic. But I mean, I don't have much to comment on the induced velocity. I know it is important indeed because, well, it will change the local air velocity that each blade will have. But well, for this project, I don't know if I still don't have an opinion if that would be really.
Okay, so I would have a second question on models. So you have the simple control model, the one you use for the control design. You have a more sophisticated simulation model. You did a lot of flight tests, so you have a lot of data. But from what I understand, you didn't try to do some kind of model identification, or try to see if your simulation model is a good model in some sense. So again, maybe it's just a question of time. You didn't have time because you already did lots of things, so that's fine for me. But do you think it would be interesting, useful to do this work? So can you comment a little bit about that?
Yeah. So indeed, the model that we're gonna use, and then so the parameters actually for tuning our model for the control, and that we're also going to use in simulation or to kind of to be able to test our algorithm in practice. So these parameters, well, first we had like crude estimates. From flight tests, we could get some ideas of more or less like not, I would say, not like take for example the coefficient C0 and C1. We actually the idea there was basically to estimate these using NACA measurements and basically match the values that we can find for similar wings with similar dimensions in terms of area and also aspect ratio in order to try to find what would be probably these coefficients in those cases. In some flight tests, we could turn off the motors and try to make a glide. In that sense, try to deduce these coefficients, C0 and C1. And another, actually, I would say maybe a more important parameter that we evaluated in the flight test was where we would estimate to be the zero lift plane. So this we would do in practice, basically accelerating the aircraft and observing if we change the reference frame of the aircraft, if the aircraft would have a tendency to climb or to descend. So I would say this was probably the parameter that was most important for us to be able to make it work out in practice. While the other parameters, we could actually make it work out with only a notion of the order of magnitude that it is in reality. So, for example, the derivative of the lift coefficient, we actually just choose a lift coefficient that was reasonable given NACA measurements. But I would say, indeed, if we can have these parameters like more well identified, we could also maybe get better performance for the aircraft. This hasn't been done yet. If we can identify this, I think it's another thing to evaluate. The good thing about simulation is that in simulation we can more or less have control of these modeling errors. So I mean the difference between the simulation model and the control model. So in the sense that we can tweak a bit the parameters there and see how it behaves, and to see if we are actually robust to the fact that we don't know those parameters. But yeah, so I think like to summarize, and the knowledge of these parameters could eventually help the performance, but they're not really essential. So I think that was probably why we didn't do much more about that.
Okay, so we have a few questions more on control, but so more on really on the core of the contribution. If you can go back to slide 42. Maybe the main slide.
Sorry, the 42.
I have 42, maybe it's 24.
Oh yeah, yes.
No, later.
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 Later. So after this one it's the end of the.
Okay, you don't have extra slide. So anyway, so that's not very important. Okay. Yes, you can stay here.
Okay.
So am I correct that so basically at very low speed you control the pitch, and then after some threshold on the air velocity you control the angle of attack. So it means that in theory you can have basically discontinuities of the desired pitch angle, right?
Yes. The desired angle of attack.
Well, yeah, the desired, yes, or
sorry.
the desired pitch angle. So is it something that you encountered in practice? Can it be a problem? Would there be a way to avoid this discontinuity?
So just so I get clear, to avoid the singularity that I have before? Okay.
It's not a singularity, it's a discontinuity.
Okay, so going from this low speed control to this high speed control.
Yes, basically when you start controlling in angle of attack instead of controlling in pitch.
Yes, I see. So if you could avoid this, well, I mean, I don't really see it as a discontinuity in that sense, because we're associating still to that frame that we have the pitch, an angle of attack. So that means that the angle of attack is actually evolving in a continuous way. So yeah. So what we have there. So this is the frame for the low speed, and as I said in this other slide here, we're going to start aligning the aircraft in order to get to a balanced flight in that still low speed flight domain. And so if the aircraft is in balanced flight, then we'll actually be continuously changing the angle of attack from that angle of attack at low speed that we'll compute using that formula over there to the angle of attack at high speed. So from that point on, it's not discontinuous in terms of the pitch angle or the angle of attack. So maybe if I come back to this graph that I had before. Sorry. Sorry. Yeah, was sorry. So at low speeds, we're gonna have the pitch equals to 0, right? But as soon as we can have this balanced flight condition again, when we add the second vector j in order to align this aircraft, to align the aircraft to the balanced flight condition, then we start computing this associated angle of attack. And once it gets out of that zone, it will continuously change from the low speed angle of attack to the high speed angle of attack.
Another question, practical question.
Yep.
So at low speed, the yaw is free, right?
Yes.
So it means, for example, with this guy, if there is some wind, it will align naturally in the direction, so noise up toward the wind.
So remember, we're in the neighborhood of near the singularity, so where the air velocity is 0.
Yeah.
So if we have a gust,
Not always exactly.
yeah, but indeed, if we get surprised by a gust, the aircraft will.
A little bit of wind before you start controlling in angle of attack. I mean, you still control in there's still some zone in which your yaw is free. Okay.
Yeah, there will be a short zone where the yaw will be free. Yes.
And for example, if at this moment you decide to fly toward the wind. I mean, basically not
yeah.
with the nose in this direction, but at the P.
At
P radians. You see, basically you want
orthogonal to the wind.
No,
sorry.
Not orthogonal to in the direction of the.
In the direction of the wind. Okay. Yes.
Not facing the wind, but wind back. Okay.
I'm sorry, I didn't really understand. The wind on the tail, so blowing from behind.
Yeah.
Oh, okay, so if we had the wind coming from behind, if we want to fly in the direction that is, I see.
Yeah. So basically, how does it work? Can you explain a little bit how does it work in this case?
So it will all depend on the velocity of the wind and the velocity of the aircraft where we're going.
Start, basically, you're stationary. You have 2 meters per second wind.
Okay. Blowing from behind. From front?
Yeah, from front. And then suddenly you decide that you go back. So basically you have a reference velocity which tells you that you want to go in the same direction as the wind is.
So in that case, the aircraft will face the wind?
Yes, it's already facing the wind.
Yeah, so it's already facing the wind because but at the same time it's going to move backwards actually for this first part of the motion. And then once the air velocity direction starts increasing, it will then start aligning slowly with the direction of the air velocity. So once we surpass these 2 meters per second, it will start aligning itself to the direction of the air velocity. So it will really move backwards at first, but then it will start aligning itself with.
And even
with the nose pointing. I didn't put here, but we did some experiments where we would do a circle, for example, and the yaw of the aircraft would be basically constant because the air velocity was blowing in a given direction, but the trajectory asked it to actually the velocity, the desired. Let's say the control of the translation motion was requiring a circle, and that means that the velocity, the inertial velocity of the aircraft was actually moving, and sometimes actually opposite to the direction of the air velocity, of the whole air velocity vector. So the vehicle would basically move like a quad with a constant yaw direction.
Okay, and maybe to. The small questions. Maybe I will be the last one because
it's not me. I don't have any problem. It's you. Okay.
Do you think so? So basically, there is no planning. I mean, in the control strategy. Okay. Do you think there would be some interest? I mean, to introduce some planning.
Okay, so when I understand when you say planning is you mean like a preferred way to use the motors or the aerodynamic force,
but also some kind of feed forward.
So,
high level feed forward.
A high level. Could you maybe
basically if you have a wheeled robot.
Yeah.
If you want to go from this point to the back of the room, you will not just have some feedback. You will have some planning. You will plan some motion, and then you will put feedback on that.
Yeah. I really don't know actually how this could be well, how this could be actually helpful for a convertible vehicle at first moment. Yeah, I don't know. I would have to think a bit.
All of vehicle is a planning. There's a
Even if you have
yeah, I know.
So yeah, I mean, in a certain sense, I think we already get to control the aircraft's translational motion and even have some secondary objective in the orientation. So I really don't know really how this could be.
Okay, thank you. So that's good for making again congratulations.
Okay. So thank you, Pascal. So the next one will be Abdelhamid Taïbi, who is online. So I hope you can hear us and.
Okay.
Hello, Hamid. Can you hear us?
Hello. Yeah, very difficult to hear you guys. So can you hear me?
Yes.
Perfect.
Okay. Thank you very much, Thomas, for this nice presentation. I really liked your presentation. I also enjoyed reading your thesis, although there are a few places where I think it needs some smoothing and some cleaning. I actually highlighted a few things. I will send you the thesis later for for further cleaning. There are some places where I had some difficulties understanding, and also for the reader to understand what you're writing. Sometimes, we see a control, but we don't see the details on how to implement this control, for example, in terms of what do you measure, what do you estimate. We see vectors like this, but it would be interesting, after giving an algorithm to summarize how, for example, you would implement that. What do you measure? What do you estimate? Okay. I'll give you a few examples later. Now, my first question is, on the concept, for example, why did you choose to use this representation of frames, okay, I, J, K, instead of using a compact, using the concept of orientations on SO3 and having some compact algebraic formulations? Why do you pick this framework?
Well, thank you for your question. Well, actually this framework is mostly for well, you mean also in the thesis, right? But
yeah,
this choice of the notation I, J, and K it was actually something that was done previously in the works here in I3S. I find it's just an easier way to basically explain the concept that we're using here in an Euclidean vector for representing the Euclidean vectors to represent the orientation of the aircraft. But I mean, we could still write it in using a rotation matrix in a compact SO3 framework. But
yeah, maybe an equivalent, for example, giving the control in terms of IJK and then giving the equivalent compact formulation would help readers that are familiar with those notions. Sometimes we see in your control we see IJK, okay, now those need to be estimated or measured or but it's very difficult to see how right? I'll give you an example later on using the K bar, and sometimes you use K bar and then you use the derivative of K bar. Okay, I was a little bit puzzled on how are you going to do that? How are you going to, for example, get the K bar? Let's see, for example, in page Do you remember, do you recall the page where you use K-bar in your?
Yes, I can just open it here.
Maybe you can share with us the page where you have your.
Yeah. But yes, I think I know what you're talking about. But indeed, because we so when we give the definition actually of what of the desired K-bar, it will be dependent on the vectors that we use there in the translation control. So usually when we have a derivative of one of these vectors, it means that we want to have the derivative of the desired vector, which is a function of those vectors that we defined there in the translation control. So maybe if we yeah, sorry if I go
Yeah, page 58. Maybe
50,
can I share with you? Maybe I can
yes,
share.
yes,
or
yeah, you can share.
Can share the document. Okay, so let me share.
Yeah, there you go.
Okay. Can you see here?
Maybe I have to stop sharing, or no, maybe.
Yeah, this is.
Oh, okay. I can see you now. Yeah.
Okay. Yeah. So so in this control here, okay. So you're using K and K bar, okay, and then you have omega bar that depends on K bar dot, okay. Now I was wondering how do you get the K bar dot?
So so if we go, so the K bar has a definition, right? That was given a bit before there, which is the expression that we use for the desired K bar. And the K bar dot, actually, we can obtain it using a
So K bar is basically D over,
exactly.
okay, that's the direction of D. And your D depends actually on the acceleration. And so, you know, it requires some derivatives. You need to differentiate the acceleration and things like that, right?
Yes. Yes. So
that's what you do?
Yes, yes. So in an implementation, we basically
you differentiate the measurements of the accelerometer?
No, it's not really the accelerometer in that case. It would be
no. This is the accelerometer and the velocity, right?
No. Actually, on your left there's a equals to m psi minus g. So the psi is the control, the PID control that we design in order to control the translation of velocity. So it's auxiliary control vector. And well, J will be the direction of gravity. Its derivative will be 0. In the case of the air velocity there, yes.
So you're differentiating this?
Yes, we're going to differentiate that.
But Xi is the control. How can you differentiate again the control?
Well, so the control would be basically we'll numerically differentiate our PID control. For example.
Okay. Another thing related, you know, that I see here, in your control, you don't compensate for the gravity, right? So you use the integral to overcome the gravity. Is it correct?
No, actually, this minus g that you see there is actually this compensation of the gravity.
So no, in designing this Xi, okay, you don't compensate the gravity. Because you know, if you go to
in designing the Xi, we don't.
You don't compensate the gravity in designing the Xi. So basically, if I understand, you include, you know, all the perturbations, including gravity, and then you hope that your integral action would compensate those perturbations, right?
No, wait. So let me just be clear. So that minus g there, that's inside the vector A. It's compensating actually the gravity action. The Xi is only used to design the control of the problem v dot equals to Xi.
So see the control 3.7 does not compensate the gravity. So you have, you know, just you
Yes.
hope that this integral compensates the gravity. No?
No. So in order to arrive at the equation V dot equals psi, we actually already compensated the gravity by setting the thrust inputs to the values depending on A, D, and E.
Okay.
So
Okay.
if you let me share for 3 seconds,
Yeah, go ahead.
Let me. So if I go down to the presentation here, so if we go, back to this slide here, so here we have the equations of dynamics. We substitute our aerodynamic model. So here we see we have the gravity direction, and actually we can rewrite the same system before. So we depart from this system here where we did not change anything. We just added and subtracted this auxiliary control vector there. And if we define the thrust inputs by these expressions here, depending on D and E. So you see D and E depend on A and depend on the gravity direction G here. So actually the compensation of the gravity direction is happening inside of this definition of the inputs of the thrust and the vector J over there.
Zero velocity, zero angle theta, and check that T is equal to mg. In that case, the thrust to compensate directly from the.
I can't hear, eh? I don't know.
Claude is suggesting.
Claude? Okay.
If we look into these inputs here, we're going to see that the gravity will be compensated. It will be inside these inputs, right?
Okay.
It's somehow encoded in there.
Okay.
It's from the first equation anyway. If you look to the first equation, mv dot is equal to m psi minus m psi plus mg and so on.
Okay.
You keep the first term psi and you put the other terms equal to 0. And you see the gravity is already there.
Okay.
Yeah.
And, it's just a way of explaining it. But anyway.
Okay. No, because when I see the model, I see D as staying there as a disturbance somehow. If you go to the model in the thesis, you know, you have the D as, you know, staying there as a disturbance. But here I see that everything is compensated and you have V dot equals C, and that's fine. Yeah. I was worried because my point is, you know, for example, I was going to ask a question. What would be the difference between, you know, applying your control to small scale UAVs and applying your control to large scale UAVs? What would be the difference in your opinion? You know, would your control scale easily to, you know, large vehicles?
Well, so we haven't really thought about upscaling things, but I think one of the main problems we have is actually the capability of actuating fast a large vehicle like the ones we have here. But I mean, from a purely control point of view, I don't see much of a problem. And well, we just basically worked out with the small aircraft that we have here, which is
different of scales.
Which and yeah, we did work with a larger aircraft, which is for example, the cruiser and the fighter aircraft. I'm sorry, but you maybe can't see it here today. Well, I can't really turn my camera, but this aircraft here, for example, is twice the size of the other ones over there. But I mean, moving on to large aircrafts. And yeah, the weight as well. I mean, it's really another order of magnitude of aircraft, but like it's. I mean,
do you think that, you know?
Larger.
Do you think that it's you know, why we don't see those type of vehicles common? Do you think that is due to a technical challenge in the control, or it's maybe related to other things in terms of cost and efficiency? And is it a technical challenge that preventing from, you know, getting those type of convertibles at a large scale, you know, being manufactured? What do you think?
Yeah, I would say there's definitely a control challenge there. And like, for example, the vehicles that I showed in the beginning of the presentation, they are some of the very few that have reached this operational phase. And if we look into various articles that were developed for these aircraft, that were developed, why these aircraft were developed, we'll see that these technical challenges are always there. However, I think maybe a very important thing in terms of scale for these smaller aircraft and the larger aircraft is actually the robustness to wind perturbations, because it's as if these smaller aircrafts were like always flying in a sort of a tornado, because the wind perturbations are actually quite close to the velocities that they fly during the transition. So in a certain sense, I would say that we have a very large challenge in working with these smaller aircraft. So if we can work them out well, we can then maybe scale this up to larger aircraft, where these problems are a little bit less severe. But yeah, so I think in terms of as far as scale goes, that's what I can see from what I
Okay,
did in
thank
my
you, Thomas. That's all for my questions. I really enjoyed your presentation and your work, and I have some I highlighted and, you know, some uh, typos and stuff in your thesis. I'll send you the thesis later to I think the thesis needs cleaning. Okay, so, you know, if you have a nice work and then you shadow it with a thesis that's, you know, full of mistakes and stuff like that, it's unfortunate. Okay.
Yep. Thank
Okay,
you. Thank you very much, Brian.
So next I give a stage to Daniele. Daniele, can you hear us?
Yes, I can hear you. I hope you hear me well.
It's your turn.
Yep. I hear you well. Yep, we hear you well.
Okay, so thank you very much, Tomas, for the nice presentation. I also enjoyed a lot your work, and some of this was somehow a flashback. So coming back few years for me, and I wanted to thank also Claude and Tarek and for inviting me. It was also nice to see some of the jury members here. So, you know, being the last of asking questions, also happens that many of the questions that I wanted to ask have been filled. But I wanted to come back to this issue of, no issue, but let's say topic of models. So concerning the model part. So, and the estimation of the aerodynamic coefficients. So basically, this I think it was touched also by Pascal, but so if I understood it correctly, you did not estimate these coefficients by having your data, right?
Yes. We tuned them, but not like, let's say, an identification procedure to really.
Okay. And besides, let's say, the specific identification of the coefficients, did you by chance also evaluate the residuals? Because I mean, you have your model, which is composed of coefficients, no? And then there might be, let's say, other components of the models that somehow have not been taken into account by the model itself. So the question would be, did you by chance take a look at the residuals with respect to the models rather than the coefficients themselves, or basically this was not done, just as a curiosity?
In the beginning of my thesis, I did evaluate a bit, let's say, what the model would predict in terms of aerodynamic force and what we would get from a bit from the accelerometers, and compare it with what we would get from the accelerometers. And well, I tried to kind of find something out of there, but well, it's something that I saw that with the amount of data I had, it was still not enough to really do a good identification on that side, at least not in an easier way. in an easy way. So I really didn't follow that axis during this research. Yeah.
Okay, don't worry. I just was curious if you took a look at the residuals. So then I don't know if you can go to slide 26, if
Yes.
yeah, because I was intrigued by by this study, which is also related to the other point I wanted to touch, which is induced velocity, but then you already answered. So, I don't know if you somehow can have some, can tell us a little bit your practical sense with respect to of how much then the control surfaces would change the main expression of the aerodynamics itself. Because I mean, here basically the control surface is changing the lift, no, and the drag. So, and also, what is somehow your feeling? What is about this? So, how much is it important that the next student should take into account the relationship between the contour surfaces and then the main aerodynamics effects? So, in terms of torques and forces. So, I just want to have this feeling from you.
So as far as the control model goes, we do not take into account the change of the the change of, well, the motion of the control surface will change in terms of the model of the aerodynamic force of the aircraft. Because in theory, when we deflect a control surface, we're actually also changing the zero lift plane of the model. So this was not something, let's say, this effect is not really included in the model. The way the control was designed is actually should actually be capable of being robust to these perturbations. But I would say it would be maybe interesting to investigate, especially in configurations that are maybe very dependent on, like, they have large control surfaces, what this effect could bring, and maybe try to maybe even propose a model that could compensate for these fluctuations that you would have in the lift due to these. But, well, in any case, for what we saw in practice, even though this will change, will change the aerodynamic force of the aircraft, will change the zero lift plane of the aircraft. It still wasn't something that would impede us from being able to fly as we wish.
Okay, yeah, so this connects to the robustness of the controller, which we will touch in a second. So the other question I had was in slide 28. So yeah, concerning this model, some of the, I mean, I think that here the underlying assumption is that you can apply the superposition principle, right? Yes. So, I mean, also here, I don't know if you can tell us a little bit more about your feeling of how much this is, let's say, what are the, because I think that this is valid for a certain number of flight envelopes, okay, and then it's not valid for others, which is basically a possible barrier to a, let's say, global controller, no? Because then if
Yes.
So I just wanted to have your feeling about and your ideas about this point. So how much then, let's say, this model, which is based on superposition principle, then is a barrier towards the global properties of the controller.
Yeah. So indeed, when we apply these models with the disks and the fuselage, we're taking into account the superposition principle. So we're not taking into account interactions that we know that actually happen between the wings and other surfaces, and also the motors and the aerodynamic surfaces. So well, I know this is well documented in aeronautic engineering. So, and this really something that's taken into account in dynamics models of airplanes. However, well, airplanes, we can sometimes assess this, well, we can compensate for these effects by adding some linearized terms to the aerodynamic coefficients, and well, where we're actually going to use some methods that are semi-empirical that were developed by the NACA in the 20th century. While these methods could be eventually applied to compensate that, in the case of convertible vehicles, these methods actually don't really apply that well, because we're actually going to encounter large angles of attack. We're going to encounter an interaction between the motors and the aircraft's airframe, with the motor with a large inclination with respect to the wings. So all of those traditional methods that were usually used in aeronautics, that at first that was probably the first thing that I thought of maybe trying to as a way to improve the simulation model in order to take them into account. They were actually not applicable. And as far as I saw in the literature of aeronautics, they're still, I mean, we still don't have like a simplified model that we could apply that does not involve like CFD or something a little bit more heavier in order for us to run to test the control of a drone like the ones we have here. But yeah, so I think indeed this would be very important. We had some drones that had some strong interactions between the motor and the wings, and we got to that conclusion after a lot of observation of the flight results and comparison also with the simulation. So we saw that things weren't matching, and so yeah. So I think indeed, if we could like even from wind tunnel data, identify a bit better these relationships, we could maybe improve the model. But yes, the model is very limited with respect to that aspect.
No, okay, so it was nice. So basically, you experienced basically this, and you had a feeling that basically for some cases you have cross interactions. Because I mean, some of the work that we're doing here is wind tunnels actually also shows these parts of unsteady effects. So another question that I had was concerning the control. So can you get back to slide probably 13? And apologies if I got it wrong, the slide, because I don't remember. Yeah. I think that 13 was okay. Yeah, 13.
Okay. Yes.
So please tell me if I got it wrong, because I might say things that are not really correct. So basically, in the longitudinal dynamics, in the plane, assuming that you're moving the plane, you get two independent inputs: the thrust, the total thrust, and theta. And this allows you to basically feedback linearize the XY dynamics. And then basically with the angular velocity, you try to zero the lateral component. Is this the sense of the controller or not? I mean, is this the underlying property of the system or not?
Yes, I would say that that's in high level speaking, it's really kind of the objective, because well, we want to, as you said, eliminate with the angular velocity or the control of the orientation of the aircraft. We want to eliminate this component here, and we want to put all of those external forces in that plane, and where we can actually we have a degree of liberty there, because we can also for the thrust input, we can actually set it in many ways with respect to the body frame. So we could choose the thrust with a tilt angle on one value, but we could also choose it with another tilt angle, which will give us another orientation for the aircraft. So basically, we have these two things to work with: the aerodynamic force and the thrust force. And yeah, so basically we're throwing all of the external forces in that longitudinal plane in order for us to compensate them using these forces. So the control of the aerodynamic force comes also from the control of the orientation in that case.
Okay. Yeah, because basically this decouples the dependence of the aerodynamic force, which depends on the orientation, with respect to the control inputs, right? Because then you have the thrust, and theta, which are independent with respect to the orientation itself, which causes variations of the aerodynamics effects. So this is yeah, okay, yeah, that's clear. So yeah, this was the geometric interpretation. And then the last thing that I was also wanted to touch was concerning planning. This was also mentioned by Pascal, I guess. I mean, what's your feeling? Because I mean, my high level understanding is that planning might be also useful for somehow avoid situations where the model is not really determined, like if you pass close to the stall. And so do you think that this would help or no? Actually, the planning having somehow a predefined trajectory which might avoid some potential singularities, like if I remember correctly, you get this singularity when E is equal to 0 and the acceleration
when VA equals to 0?
yeah, no, also E, the value E in the controller, the E, which is you add on 2 of, yeah, which clearly then brings theta a little bit to the border. So I don't know if your feeling is how the predetermined trajectories might help in getting away from possible singularities.
Yeah, I mean, let me think. Well, a predefined trajectory, I mean, I think could be interesting for example, evaluating if we would reach saturation of the motors or something like that. We tried to control the aircraft in order to have a small angle of attack, but then again, it could happen that a given trajectory will have a large angle of attack at a higher speed. Usually the high angle of attacks that will happen at low speed. We can't avoid that, and that's not really a problem because the aerodynamic force won't be large at that phase. But yeah, I mean, the model, it's actually more precise we tuned it in such a way that's more precise at low angles of attack because we can actually compute the C1 coefficient, the one that is actually used to compute the C0 bar. I actually have a slide for that. So for example, we can compute so this is basically the curve that you showed in your thesis as well. So for the lift coefficient of the model, and this is, for example, an aerodynamic data that we have here. So we can choose this C1 in such a way that we match very closely the lift coefficient using the model at low angles of attack. So yeah, I mean, we tried to, we would like trajectories that would fly in this zone as much as possible, especially at high airspeeds, in order to avoid, because we know that the control model will work better at that phase. So in this zone of the angles of attack. So yeah, I mean, flight planning could probably help us do that and also avoid saturations of the motors.
Okay, so Thomas, I'm done with my questions. So thank you very much once again for nice work, and yeah.
Thank you very much for your questions.
So highly message to Murat. I think you are
very
so
very
answer shortly, very short answer.
First of all,
answer 2 sentences.
thank you very
Yes.
much.
Okay.
And
I'm sorry.
congratulations for the real flights as well. So I have only one question actually. Very quick.
And answer 2 sentences.
I'll answer in 2 sentences.
So think about you're flying, this is your wing, this is your propeller. So you start increasing the speed forward. So you're going to tilt probably the motor. And at the point you're going to go up to, let's say, maybe 80 degrees. This is what I have seen on most of the flights. I have never seen 90. Would your controller be capable of doing it more than 90 in order to be capable of giving lift possibility to the wing portion so that you will fly efficiently with these vehicles or not? That's the one question.
Okay. Just so I make sure, basically saying, will the controller at some point become completely a plane in the sense that we have the motors
forward, even positive, because if you put the motors more than 90, such as 95, that will give you the possibility to tilt angle of attack of the wing positive, so that you will start generating real lift with the wing portion and start flying efficiently. Or will you be really limiting the motors up to 90 degrees and you will never be
putting slipstream more than, let's say, zero angle of attack?
I see. So actually on the assumptions of the controller itself for the definition of the thrust, we don't take into account the limits of the thrust vector. But when we go distribute the thrust force among the aircraft, we have to take into account the limitation, the saturations of the vehicle. So if we could produce this this tilt angle more than 90 degrees, yes, but I mean I'm not sure if I understood well.
Is it limited?
Yeah. I mean, all of these vehicles here, I did not mention, but they also have saturation limits on the tilt.
Okay.
So if we could, we would, I mean, produce, because that would mean we could go probably down at the speed, the acceleration higher than the acceleration of gravity, and minus the aerodynamic drag. But yes, so.
So thank you. So I would have a question, but we are really in a hurry. So just to congratulate for your presentation, it was very clear. And I leave a stage to Tarek and after to Claude for the final words.
Okay, so thanks, Thomas, for your presentation on staying with us for 3 years and do a lot of experiments and so on. So I will not ask you or not do something else. I will not answer to all questions, but I will ask you just to do something. You prepared, I guess, the simulations in order to show to Pascal there's way to how to counter the wind and how to do the simulation with the wind. You know all of this.
Yes.
You can show them later on, or maybe if you prepare the simulation, you can show them just before. Because we have to leave after 2 minutes.
Yes.
In order to write a short report. Okay, when you come back, show them something about simulation.
I'll
be happy to show.
Pascal this morning.
Okay.
Not enough, I suppose.
Okay, no problem. Okay, I leave Claude, so he did a lot.
The final word.
Final word. Well, independently of Thomas' work quality, I would like to point out the quality of his companionship during these 3 years that we spent together, and the quality of his companionship, and that I will probably miss when our roads will depart soon. Thomas make me think a little bit of this fable of La Fontaine. It's oak tree and reed. He's a reed of good humor. He's always always smiling. I mean, receiving advices or remarks with a smile and always positively. He receives advices the same way. He never breaks. He can bend, but like the reed, he doesn't break. And this is, I would like to thank him for this relationship that we had, and for his qualities also that he had, human qualities.
Thank you very much, Claude. It means a lot.
Thank you. So now we have to deliberate. So
because they have to leave in 15 minutes or 20 minutes maximum.
Can you please leave and then so we minimize the time.
Tarek, is Tarek in a room?
You can keep the connection.
No, I'll just.
Hamid is there. She's there.
Yeah.
I'm just gonna stop I have a live
person on which guy is the third one? That may be you, right?
Batch, can you call Tarek to help me? Actually, I'm just gonna. Oh, I found it here. I'm just gonna cut the live stream because